Hi and welcome back to Spherical Chicken in a Vacuum. Today we are going back to the lectures on material science, and since we are just at the beginning of the story, it's better to start from the basics. And the basics of material science are in chemistry, and especially in how the different atoms interact with each other. So I guess you're familiar with the periodic tables of elements. We will not discuss this thing in details, but we will discuss a little bit about the properties of different elements. So, how do atoms bond together? Well, there are different styles, different bonds they can form. One of the main ones is the covalent bond. In this case, one atom that is missing some electrons to have a stable form, to have 8 electrons on his outer shell, is in desperate need of electrons. He finds another atom that has the same desperate need, and together they share enough electrons to be both completed, to be both stable with 8 electrons on their outer shell. This bond is very strong, and it's also quite tough. And in this example, we have chlorine, which has 7 electrons on the outer shell, which means another chlorine, another 7 electrons on the outer shell. If they share 1 electron each, they can almost feel like they have 8 electrons on their outer shell each. On the other end, there are ionic bonds. In ionic bonds, one ion, which is in excess of electrons, finds another ion that is in defect of electrons, and he decides that he can give 1 electron, 2 electrons or more for free. And this creates a bond that is very strong, and it also generates electrostatic forces between the two atoms. Then there is the most socialist of bonds, which is the metallic bond. In the metallic bond, the bonding between the electron and the nucleus of the atom, the outer electrons and the nucleus of the atom, is not so strong. So the atom does not really care about what happens to the electron. The electrons are in this cloud that can be freely shared among the other atoms in the material. So if I apply electric potential on this material, I can freely move this cloud of electrons from one side to the other, and this generates an electric current. Now, here on the right, I put something called bond strength, and you saw that for ionic and covalent bond, I put the maximum amount. And you might wonder which is stronger between covalent bond and ionic bond. And that's a game I don't want to take part to, because it's very complicated and it's on a case by case basis. Sometimes covalent bonds are very strong, sometimes they are very weak, sometimes the ionic bonds are very strong, sometimes they are very weak. Also, it depends on the condition, because if we are thinking about melting a material to break the bond, it's one thing. But if we put sodium chloride, which is salt, by the way, in water, the bond is easily open, right? So strength is a concept that needs a little bit of clarification, but even if we clarify what we mean by bond strength, which usually is the energy that it takes to break the bonds, there's no clear winner. There are distributions with strong and weak on both sides, and I really don't want to go in the details and pick a winner. Okay, if you want to do, you can go on internet and fight your own fight, because there's plenty of places where this discussion is still going on nowadays. Next one, hydrogen bond. In the hydrogen bond, one hydrogen that is bonded with a covalent bond to an electronegative atom, like oxygen in this case, finds another oxygen or another electronegative atom and finds it very attractive. So much attractive that it feels like a weak bond is formed between him and the new electronegative candidate. They will not really bond in a covalent bond, but still, this kind of electronegativity based attraction is still present, still there. This is not very strong, not very weak. It happens in a lot of materials, and we will discuss about it a lot in the future. Next one, dipole-dipole interaction. In the case of dipole-dipole interaction, you have one polar molecule that finds another polar molecule. They align, they're basically just magnets. They have the plus side and minus side. If you try to put plus and minus together, they will not stick. But if plus and plus together or minus and minus together, they will not stick. But if you have put plus and minus together, they feel the attraction. This is just the same situation, and this goes because these polar molecules have different electronegativity between the atoms that form the molecule itself. Okay, so basically small magnets if you want. And the last one, which is also my favorite, is the London dispersion forces. And London dispersion forces are very temporary. And if you think about all these electrons running around in the outside of the atom, sometimes they are more dense on one side than another. So the density is not always constant. This generates some very small, very temporary interaction between nuclei of one atom and the electrons of another atoms that maybe for a brief moment were more dense in a specific location. Well, there's much more to discuss about London dispersion forces, and I'm not qualified enough to go into details of this, but they're interesting and they also almost useless in material science. Well, they have specific applications, but for most of material science, they are not very important, so we will probably not discuss about them in the future. Still, love them. And let's take an example of material, silicon carbide. Very strong, hard material, great for many applications, metal cutting, etc., etc. What happens here? Silicon has 4 atoms on the outer shell. Carbon has 4 atoms on the outer shell. So if every carbon connects with 4 silicon, and every silicon connects with 4 carbons, they can share electrons together and go to the stable form of 8 atoms on the outer shell. This means that silicon carbide is the perfect candidate to be a covalent material, right? Well, almost. If you do the calculations, and we will speak about them later, you will see that there is a tiny bit of ionic there. Why? Well, we will discuss it in a minute, just bear with me. Let's take another example, the opposite example, a beautiful example in material science, which is zirconium oxide. In this case, to complete the outer shell, zirconium has to donate 4 electrons. So it can do this with just 2 oxygen atoms and share and give away 2 electrons to each of the 2 oxygen atoms. And this will make oxygen complete and zirconium complete and everybody happy. This sounds like the perfect examples of ionic compound. In reality, there's a 33% of covalent, meaning that there is 33% of sharing, let's say. Not exactly, but there's a 33% of covalent characteristics in the bonding of zirconium oxide. Again, why? Everything is sounded so nice, so clean. Well, because we humans like to put things in specific boxes. So we like to put everything in the box of ionic bonds, in the box of covalent bond, in the box of metallic bond, and keep them separated as much as possible. But in reality, we can have 100%, almost 100%, basically 100% covalent bonds, but most of the materials are mixed. They have a little bit of ionic, a little bit of covalent mixed together. That complicates things a lot, and we need to discuss a little bit about something else. So when we represent sodium chloride like this, we have the extra electron of sodium that jumps to the chlorine. Okay, everything looks perfect, and even if the electron now is very attractive to the chlorine, it still feels some attraction to the original sodium nucleus. If we change representation, we can have a better idea of what is going on. Let's think that this almost transparent shell is the cloud of electrons. And in this case, the cloud of electrons is not as perfectly round like it's represented here, but because of the partial attraction of chlorine to sodium, or the electron of chlorine to sodium, there is a distortion of the electron cloud of chlorine. Okay, so this distortion represents the portion of covalent bonding. In the chlorine-chlorine, which is a non-polar covalent material, we have a better, more deformed electron cloud, as you can see in this example, very simplified example. And this is even more extreme in the polar covalent bonds, like in the case of chlorine with the hydrogen. And in the bottom, I removed the nuclei because otherwise there's no way to see the hydrogen cloud. So just makes it more simple for me to represent. But think of it like it's the same example of chlorine in the top. Okay. And then we need to discuss about electronegativity, which I mentioned many times here, and I never discussed in detail. Electronegativity can be measured in many ways. Well, we have different scales to measure the electronegativity. And it usually goes from, in all scales more or less, it usually goes from the bottom left with the lowest values to the top right with the highest values. This is Allen scale, but there are others, and starting from Pauling, I think, which was made, I think, in 1938. They look a little bit different, but the concept is the same, and we can use these electronegativity values to draw this nice graph that I think is called Norman triangular diagram, something like that. And considering the absolute electronegativity, the difference in the electronegativity between the two atoms, and the ionic character of the bonding, we can determine if they're ionic, covalent, metallic, or in the middle somewhere. Of course, if it's the same atom like fluorine and fluorine, it can only be covalent bonding, right? And if and in the case of fluorine, there is a sort of strong bonding between the atom and the electrons surrounding it, because the electronegativity is very high. So the electronegativity represents this strength, this force. In the case of metallic materials, the bonding between the nuclei and the electrons is much more loose. That's why we have conductivity. So in the case of cesium here, we have a very loose bonding between nuclei and electrons, which gives a almost completely metallic characteristic. The electronegativity is very absolute electronegativity is very low, and if it's cesium, then there is no difference in electronegativity, which makes the material completely almost completely metallic. In this case, two characteristics is that you need to take into consideration: the absolute electronegativity and the difference in electronegativity. The absolute electronegativity is very low, and the difference in electronegativity is zero, so it goes there in the corner. And then we have ionic compounds in the top corner. And real materials, most of the real materials, but these are real materials, but most of the materials that have industrial applications fall somewhere in the middle here. And from this diagram, we can sort of guess a little bit of properties of materials. Not always, there is not always this simple, but something we can guess. So if the characteristic of the material is very metallic, we have conductivity, for example. And also the material is probably malleable. It can be deformed, it can be formed, it can be shaped without breaking it. Okay. In the case of covalent bonds, we have something that is tough. materials, covalent materials that have industrial application are usually quite tough. And in the case of ionic materials, we have materials that are usually brittle because the ionic bond is the least flexible. Let's call it flexible. Is the least flexible of the bonds that we can have. Why this is important? It's important. These characteristics, but also hydrogen bonding, dipole-dipole interactions, not the London forces, not the London forces, but the others can contribute to the structure of the material itself, because this is just one bond, atom-atom. But then this bonding creates a crystalline structure. And the crystalline structure, it's an even better model to predict the characteristics of the material itself. So this is the unit, if you want. If you understand the unit, then we can go to the larger structure. So next time we will speak about the crystalline structure. Another thing is this also determines how well packed together the atoms can be, so the density. Many metals are very dense, for example. And this is determined by the characteristics of their bonding. But we will discuss it next time. I think for today, this is more than enough. Let me know if you have any question, and see you next time.